Hello and welcome to our first Lancashire Science Festival Live of 2019. Today we're going to be giving you a sneak peek at some of the awesome experiments and fantastic science that's going to be going on during the Science Festival this year. The Lancashire Science Festival is going to take place between the 27th and the 29th of June, so it's this Thursday to Saturday, and what we have is 2 days of school day, so on the Thursday and Friday, and then on Saturday everybody is welcome. And the best thing is, it's completely free. So if you'd like to attend, please visit our website, lancashire.festival.co.uk. You'll be able to find all the details of how to register. As I say, totally free. If you have any questions during our YouTube live session today, please get in touch on social media. We've got the links below. Pop us a question and we'll try and answer before the live is finished. If we don't quite catch it before it finishes, we'll get it on the next one. So please do get in touch. Now, as I say, we're going to have some fantastic sneak peeks today, and I have with me the Young Scientist Centre team, Joe and Sujata. Now,
hi.
Hello.
Hi.
So you guys are going to show us some cool things about space today, right?
Absolutely, yes.
Fantastic. Well, I'm going to hand over to these guys. You've got a treat in store. Over to you.
Okay, thank you. So, Joe, you know what I'm going to talk about today? I'm going to talk about the conditions on 3 of the planets in our solar system. And I'm going to show you the conditions on these planets and how they affect things that we find here on Earth, so things like water and the gases.
Fantastic.
Yeah, so the first planet I'm going to talk about is Mars. Mars is a close neighbour of ours, and we've got lots of similarities between Mars and Earth. We've got lots of geological features like volcanoes, canyons and valleys, but there's one big difference between Earth and Mars, and that's air pressure.
Okay.
Do you know what air pressure is?
Isn't that all about the air particles and how much pressure they push down on things?
Yeah,
Okay.
That's exactly what air pressure is. So on Mars, we've got a lower air pressure, so there's less of that pushing force on Mars. So you might be thinking, well, what's the big deal about air pressure? Well, air pressure has a big impact on how water behaves. And water is really, really important for all life here on Earth, certainly life as we know it.
Absolutely.
Okay. So the first demo that I'm going to show you is how water behaves on Mars. Okay. So there's been lots of missions and robotic landers that have been sent up to Mars, and lots of them are looking for liquid water. So how liquid water behaves on Mars is actually quite important. So this is going to be our first demo.
Excellent.
So the equipment here that I've got is going to try and recreate that low air pressure of Mars. So I've got a bell jar here, and it's going to be hooked up to a vacuum pump here. And I've got a squishy marshmallow, okay? And that's going to show you the changes in the pressure.
Okay, so it's squishy because it's already got air inside it, isn't it?
Yeah,
Okay.
so squishy's got lots of air in it, nice and soft. So when I pop that inside, and also inside the equipment is I've got some water, okay? And I've got a thermometer inside. So what's the temperature on that thermometer, Joe?
It says it's just over 20 degrees, so it's room temperature 20 degrees.
Yep, okay. So we've got that liquid water in there. We're going to see what effect the pressure has on that water and on the squishy marshmallow. Okay, so pop all my bits in. I'm going to try and create a really tight seal.
Now this is going to be a little bit noisy, isn't it, when the vacuum pump goes on?
It will, yeah.
Okay.
So you'll have to bear with me, a
Right.
bit noisy. I'm going to create a nice airtight seal in there, because what I don't want is the air creeping back in.
Okay.
Because what this vacuum pump is going to do is it's going to suck out all the air from inside this chamber here. So we're going to create that low air pressure. There'll be less air pressing down on things. Okay, so, okay, we're all set. Switch it on.
That tap.
Okay.
Oh, something's
Whoa,
happening.
Okay, right.
Look at the marshmallow.
Yeah. So what's happening to the
It's getting
marshmallow?
bigger.
It's getting
It's
bigger.
massive.
It's expanding, right.
I wish your marshmallows were that big.
Be great to eat. Would be great, wouldn't it, if they were that giant? But the marshmallow's expanding in there because we're sucking out all the air particles from inside this chamber. So less of the air particles are pushing down on that marshmallow. Okay, so it's free to expand.
Okay, there's something starting to happen
Yeah.
in the water as well.
Yeah. So I mean, I can see something happening if I look really closely, but it will take a few
Here
minutes.
Here we go.
Yeah.
Oh, oh, it looks like it's starting to bubble.
It's starting to bubble. So
Big
let's wait.
bubbles.
So what's happening
It's
there?
boiling.
So when
the water's boiling.
When water bubbles like that, it's normally boiling.
Yeah,
You're
absolutely.
right. Okay, so I'm just going to turn our vacuum pump off, shut the noise off. Okay, so our marshmallow expanded.
Absolutely.
And the water's boiled. But
Okay.
so I'm just going to unhook the pipe from there. So can you see what the temperature is on that?
It's still around about 20 degrees. It's still at room temperature.
Yeah. So how on earth has that happened? Water boils at 100 degrees,
Absolutely.
right? Normally.
It's 20 degrees in here.
So on Mars, it's boiled at 20 degrees.
Wow.
Yeah. But on Earth, when we put your kettle on, we have to boil it. We have to take it to 100 degrees. But here, with this low air pressure, we've managed to boil the water at 20 degrees. Now, liquid water on Mars is going to have a really hard time because the window that liquid water can exist is between 0 degrees and 20 degrees. Here on Earth, it would be
0 and 100.
and 100. So it's a much bigger window that liquid water can exist.
Right.
So the conditions on Mars make liquid water really difficult to exist. Okay. So we've created this low air pressure inside this bell jar, and it's a really tight seal. Yeah, it's not coming off that top.
Won't come
so
off.
I'm going to try and get the air pressure inside here to be the same as this room here. So I'm going to let the air back in.
Okay.
But you want to make a prediction of what's going to happen to that marshmallow when I let the air back in?
Well, it'll probably go back to its normal size, won't it?
You think? So it's going to go back to that?
Yeah.
Yeah. Okay, so let's see what happens.
It shrunk.
It shrunk, and it shrunk to a lot less than what we started with.
Wow.
Yeah.
It's a lot smaller than the original size.
And it shriveled, and that's because when it was free to, when the air particles weren't pressing down on that marshmallow, it was free to expand. Okay, so air particles left that marshmallow, but not only did air particles leave it, but moisture, the water particles left it as well. So we probably got less mass on that marshmallow. So when we let that air back in again, it was all starting to push back down on that marshmallow, and it's made the sugar structure of the marshmallow kind of collapse. Okay, so which is why it's kind of shriveled. Yeah.
There we go.
Very different to how it started off. So you can see by the air pressure, the difference in air pressure on Mars, how different things would behave on Mars. So this water, for instance, has boiled at 20 degrees. Because of that low air pressure, you need a lot less heat to make it boil.
Okay, yeah.
Okay? So Earth has a relatively high air pressure compared to Mars.
Excellent.
Okay, so that's air pressure, very important. We don't normally kind of feel the effects of air pressure because it's just all around us, and it's only by changing that air pressure, lowering it in this case, that we actually get to see the effects of air pressure.
Brilliant.
Now, the other things about Mars and Earth, like I say, they've got lots of similarities, but the other big difference is the temperature on Mars. Mars is really cold, so the temperature range on Mars is minus 125 up to 20 degrees.
Okay. So it's a lot colder than
It's
on
way
Earth.
colder than
Wow.
Earth, isn't it? Yeah. Now, both Mars and Earth have polar ice caps, which, you know, both at the north and south poles, okay? But the ice caps on Earth are made of water ice. Now, on Mars, they're made up of water ice and something else that is normally a gas here on Earth.
Okay.
Okay, so I'll give you a bit of a clue. It's a gas that we normally breathe out.
Carbon dioxide.
Carbon dioxide,
Right.
fantastic. So, I've got carbon dioxide, but it's a solid in this box.
Okay. So
Okay.
usually it's a gas in the atmosphere around us.
It certainly is. But here, we've managed to get solid carbon dioxide. And this is how it exists on Mars. It's a solid. It's so cold that what is normally a gas here on Earth is actually frozen solid. Okay? So I've got two containers here with just some room temperature water. This one's got a little bit of orange colouring in it. This one is water with a little bit of detergent in it, so it's just a bit of soap in there. So watch what happens when I put this solid carbon dioxide into these two containers, all right?
So it started bubbling straight away.
It has.
Wow, look at that.
Yeah. So carbon dioxide in its solid form does something quite unusual. It goes straight from a solid to a gas. Okay. Now the soap in here is capturing all that gas, so that when I pop the bubbles, all the carbon dioxide has been released. Okay. I've probably put a little bit too much in there, as usual.
As usual.
Yeah, you know what I'm like with carbon dioxide.
You like your bubbles.
I do like my bubbles, yeah. So in this first container, well, there's what you're seeing here actually. Carbon dioxide is colourless. We can't normally see it, but what you are seeing is this kind of mist effect. And what that is actually the water vapour or the moisture in air that's being cooled by the carbon dioxide.
Okay.
Yeah, so which is why you get this fantastic effect here. Now my bubbles are going all over the place, yeah.
So why is it sinking down like that? Why isn't it just floating up into the air?
Oh, good observation, Joe. Yeah, it's sinking because carbon dioxide is actually heavier than air. And so it's sinking and taking that carbon dioxide with it, which is why you see that kind of dropping effect.
Excellent.
Okay, so there's lots of carbon dioxide and water vapour there.
Brilliant. Being
being trapped by the bubbles there. So, like I said, Mars is really, really cold. Massive temperature range, minus 125 all the way to 20 degrees. Now, this solid carbon dioxide, the temperature on this solid carbon dioxide is actually minus 78 degrees.
Oh, that's cold.
Okay. Now, the freezers we have at home are only minus 20. So this is way colder, okay? And which is, because Mars is so cold, carbon dioxide, normally a gas here on Earth, is actually frozen, okay? And the unusual thing about carbon dioxide, as you've just seen, it goes straight from a solid to a gas. Now, we call that sublimation. That's quite a big word, isn't it? Yeah? But it simply means that the solid vaporizes. It goes from a solid straight to a gas. Now, there's not many things that can do that. Things like iodine and mothballs, they do it too, but carbon dioxide is certainly one of them.
So it's missing out the liquid state in the middle.
Yeah, well spotted. So normally between a solid and a gas, you've got a liquid stage, and it skips that because it absorbs so much energy.
That's why we call it dry ice.
That's why we call it dry ice. Yeah,
brilliant.
It's skipping out that liquid phase. So yeah, carbon dioxide, dry ice, one of the favourite things in the YIC. We use it lots. Yeah, we use it lots to show lots of different things. So that is sublimation and carbon dioxide. What I'd like to do is now I'd like to move on to some planets on the further reaches of the solar system. I'd like to talk about Uranus and Neptune. They are the ice giants. They are huge compared to Earth, and both of them are bluish in colour, okay? And they're blue in colour because of the methane in their atmosphere. Now, methane is a very useful gas here on Earth. We use it as a fuel. We use it for our gas central heating systems. We use it for gas cookers. So it's really useful because we can burn it. It means that it's combustible. It burns and gives out lots of heat.
Excellent.
Okay. So what is normally a gas here on Earth is actually it's in the atmosphere of these two ice giants. Now, I have some methane, okay, in this container here, and I'm just going to pop some methane into this container here. That, again, just has some water in it.
Right, I'm going to put my goggles on at
and
this
I should put my goggles on too.
And I'm going to stand.
Yeah, because I'm going to show you how methane behaves on Earth, okay? Give it a quick shake. I'm going to show you how useful methane is on Earth. Like it says, we use it as a fuel. Okay, so here it goes.
Whoa.
Okay.
Amazing.
So that's how methane behaves on Earth. Yeah, it combusts, it caught fire, it gave out heat. Did you feel that heat?
Yeah, absolutely.
Yeah.
You can feel it from all the way back there. Yeah, absolutely.
Yeah. So if there's loads of methane on Uranus and Neptune,
why doesn't that happen?
Why doesn't that happen? Why doesn't it, all the methane, you know, catch fire and give out loads of heat? because that reaction needed three things, okay? Now, I put my fuel in, okay? Put the fuel in. There's oxygen in the atmosphere, and I also put heat to it, okay? So we call these three things, they make up part of the combustion triangle, okay? So we need oxygen, we need the heat, and we need the fuel. So we had all three things here for that reaction to happen.
So are all those three things not on Uranus and Neptune?
They're not, no.
Okay.
So we've got methane, okay, on the planets. We've got some oxygen, okay, but what have we got missing on the planets, Jo?
Well, they're ice giants.
Yeah.
Which means it's really cold.
It is really cold. On both planets, the average temperature is below -200 degrees.
Okay.
So the heat is what we're missing, okay? So let me just show you again how methane behaves on Earth.
Can I just move it that way a little bit?
Yeah.
That's where we do it.
Okay.
Wow. So yeah, I can feel the heat coming off there. It's never going to get that warm on the ice giants.
No, we would need to it would need so much heat to try and get that methane to combust on these two planets.
Excellent.
And because they are so far away, they're in the outer reaches of the solar system, they get very little heat from the sun, and so their average temperature is below -200 degrees.
Fabulous.
Yeah.
So they're very, very different conditions in different places in our solar system.
There are, and by showing you these demos, and they are three of my favourite demos, I've been able to show you the conditions on the different planets and how different chemicals behave and how chemical reactions take place on these three different planets as well.
Fabulous.
Okay, hope you enjoyed them as much as I did.
Great, thank you.
That was absolutely fantastic. Thank you,
Yeah, you're
Sujata. Thank
welcome.
you, Jo. Hopefully you enjoyed seeing these absolutely brilliant demonstrations. So we got to see shrinking marshmallows, carbon dioxide turning straight from a solid to a gas, and then my absolute favourite. Can you remind us what it was, please, Sujata?
Methane bubbles.
Methane bubbles, fantastic. So if you enjoyed what you saw here today, then please come along to the Lancashire Science Festival on Saturday. There's going to be lots more demonstrations and experiments like this. It's completely free. You just need to register before you come. We do accept walk-ups on the day, but we recommend that you register, and you can find all the details on the website just here. If you have any questions that you want us to answer in our next live broadcast, which will be at 11 AM, please get in touch via social media. The details are below. But thank you very much, Sujata.
You're welcome.
Thank you very much, Jo. Thank you very much for watching, and hopefully we'll see you back here at 11 AM.